Hi there, folks. This is Heath. We're starting section 15.3 today. This is the section on applications of double integrals and polar coordinates. Let's begin. We've got a lot of material to cover today. For problem number 1, we're going to integrate this function, x over y, over the region that's bounded by y equals x, y equals 2x, x equals 1, and x equals 2. And so this is the region of integration here. Okay? All right. The first thing we want to do is we want to choose an order of integration. Mathematically, there's no wrong answer. But this answer is going to be easier to solve because we can do this in just one integral. If my arrow is traveling in the y direction, I always enter along this diagonal line and I always leave it along this diagonal line. But if my arrow travels in the x direction, sometimes it enters along this diagonal line and then sometimes it enters along this vertical line right down here. And that would require having to split this up into two integrals if we let the arrow go in the x direction. So choosing this order of integration allows us to do this problem just using one integral, and that's going to be a little bit faster. Okay, so now we're going to set this up. Now, my function is x over y. My outer boundaries are constants, just the largest and smallest x values we have. Those are 1 and 2. And my y-coordinate are the functions that we enter along. Our arrow enters along y equals x and leaves along y equals 2x. And now we're going to solve. We start with the inside integral. The integral, this is not dx, this is dy. The integral of 1 over y dy is natural log of y, evaluated x and 2x. And so this gives us x times the natural log of 2x minus x times the natural log of x. Now we have to integrate this from 1 to 2. But there's a trick we can apply to this term right here before we go. By the log rules, this is the same thing as natural log of 2 plus natural log of x minus x times natural log of x. And x times natural log of x cancels with x times natural log of x. And so this just equals x times natural log of 2. And that integral is a lot easier to work out because the natural log of 2 is just a constant and we can bring that out to the front. And so we get the natural log of 2 times x squared over 2 from 1 to 2. That's 4 over 2 minus 1 over 2. So that's 2 minus a half, which is 3 halves natural log of 2. Okay? So let's move on. Find the volume for the solid in the first octant bounded by the coordinate planes, the cylinder x squared plus y squared equals 4, and the plane z plus y equals 3. The coordinate planes, when we talk about those, we're talking about the xz plane, which is this plane back here, that's this wall. The yz plane, which is this wall over here. And the xy plane, which is the bottom. The cylinder x squared plus y squared equals 4 has a radius of 2. And that's this quarter circle around here. And because it's a cylinder, we travel up in the z direction, so it forms the entire wall over here. And this plane at the top is what has our z-coordinate in it. And so, it says, I'm sorry, I've written that down wrong. Z plus y equals 3. And so z is equal to 3 minus y. So if we set this up, the function we're integrating is 3 minus y. We're going to pick an order of integration. The order doesn't matter too much. Let's try dx dy, for example, see what happens. And I would say it doesn't matter too much because geometrically a circle is going to be the same regardless of which direction we enter and leave from. It's not like the last region where one direction would make us split it up and the other direction doesn't. The y-coordinate goes from 0 to 2. And then if we travel through the region in the x direction, we enter the region along this wall back here where x is equal to 0, and we leave the region along this pink cylinder here. Well, we have to write what x is equal to, and so x squared is equal to 4 minus y squared, and so x is equal to the square root of 4 minus y squared. And that will be the upper boundary of this integral. Okay? Now, all I've done so far is set this up. I'm not taking the time to solve this because I want to get through a lot of examples today. So we're going to move on. Let's look at this example. If we try to solve this, 3 doesn't look like it's very hard. The integral of 3y, the integral of 3 is 3y, but then when we plug in natural log of x, we get 3 times the natural log of x. And integrating natural log of x is tricky. It requires using integration by parts. And so this is hard to integrate the way it's laid out for us. But let's try changing the order of integration and seeing if that makes it easier. Right now, the x-coordinate goes from 1 up to e, and the y-coordinate goes from 0 up to the natural log of x. Well, natural log of x looks like that. Natural log of 1 is 0, and natural log of e is 1. And so this is the region we got here. If we set this up in the other order, dx dy, the function is still 3, but the boundaries now, y goes from 0 to 1, and x enters at this curve, but if y is equal to x, x is equal to e to the y. And then leaves along just plain old e. The vertical line x equals e. And I argue that this is going to be easier to solve because e to the y is easier to integrate than natural log of x. So let's see what happens. If we set this up as e to the y to e 3 dx, we get 3x evaluated at e and e to the y. That's 3e minus 3e to the y. Then we integrate that from 0 to 1. E is just a constant here, so this is just 3ey, and the integral of e to the y is e to the y. When I plug in 1, I get 3e times 1 minus 3e raised to the 1 power. Well, e raised to the 1 power is e minus, now when I plug in 0, 3e times 0 is 0, but 3e raised to the 0 is 3. And so the 3e's cancel, and I have minus a negative 3, which is equal to positive 3. Okay. All right. So this was an example of switching the order of integration to make the problem simpler. Let's look at some applications now. Area. Where we've been using double areas to calculate a volume, where we have an x-coordinate and a y-coordinate and a z-coordinate. But sometimes we want to just find area using a double integral. The trick in this case is that we want to then set the height equal to 1, so when we're multiplying by the height, nothing changes. Multiplying by 1 doesn't change your answer. And so we get the same thing as just the area of the base. Volume is base times height, and if the height is 1, then was 1 times the base, and we're just getting the base. And so if we set the function equal to 1, then we're actually just calculating area now instead of calculating volume. So let's try calculating the area of this region, but using a double integral to do this. Okay? And we might find that it's easier to do that than to try to find an area using the tricks that we used in single variable calculus. First thing we're going to do is going to choose an order of integration. And I would like to choose the order dx dy for reasons that I will show you in just a moment. And we'll set this up. We'll set this up in the order dx dy. My smallest and largest y coordinates on this region are 0 and 1. And then my arrow travels through the region and enters along the parabola that opens this way, which is the one that has the positive y squared term, and leaves along the parabola that opens this way, and that's the one with the negative y squared term. And since we're finding an area, I just put a 1 here for my function. This is why I wanted to choose the order dx dy, is that my functions were already solved for me in terms of x. If I wanted to do the other order, I could do that, but I would have to rewrite this in terms of y. That's not hard, that's square root of x. But rewriting this in terms of y requires completing the square. And that seems like a little bit of extra work. And so leaving the functions so that they're x in terms of y instead of y in terms of x seems like that makes sense to me. All right. And then at this stage we're going to solve. And this is not hard to solve, but I'm going to leave the solving to you so that we can move on to the next example. Okay? To find the average value of a function over a region, we have to do 2 double integrals. The integral of the average value is equal to the volume of the region divided by the area of the region. So we have to do 2 double integrals, one to find the volume, another one to find the area, but the area sometimes doesn't require a double integral. Sometimes the area is just pi r squared, or 1/2 base times height. Sometimes this might not need calculus. But we always have to do volume divided by area. Okay? So divide volume by area to find average value. Okay? So I don't know if this helps, but the VA in value is like volume, stands for volume over area. I don't know if that helps you remember it or not, but it's volume over area. So we're going to set up the average value for this function over the rectangle that goes from 0 to x to pi. So 0 to x to pi, and 0 to y to 1. So just over this region. So the average value, which the book abbreviates as V for value with a little AVE for average, is the volume over the area. The volume we're going to have to integrate. And we'll have to choose an order of integration. But if we do dy first, then this is a u substitution problem. If we do dx first, this is an integration by parts problem. So dy dx is u sub, dx dy is parts. Okay, and since most people find u sub easier, let's do dy dx. So we get x cosine xy. All right. The outer boundaries are the x boundaries, and they go from 0 to pi. The inner boundaries are the y coordinates. Well, if we travel in the y direction, we just enter at 0 and leave at 1. This is a rectangle, so nothing's crazy there. And the area of the rectangle, we don't need calculus. The area is just base times height, which is just pi. Okay. Now, I'm not going to solve this because I do want to move on to some other examples, but I'll get you started on the u substitution. The u substitution step here, if I let u equal xy, then du is equal to x dy. And so this is my u. This is my du. And then this is the same thing as, all right, y goes from 0 to 1. X times 0 is still 0. X times 1 is x. And so we get an x here. And so we get cosine of u times du. And then we'll keep solving from there. Okay? Let's move on. There are some regions that are easier to integrate in polar coordinates than in rectangular coordinates. And here's an example of one. If we did dx dy, the arrow moves in the x direction. Well, this is the x direction, and the arrow enters the region, then leaves the region, then enters the region, and then leaves the region again between 0 and 1. So we'd have one integral for this part and one integral for this part. And then we'd have a third integral for this part up here when the arrow enters and leaves the region just one time. We would need 3 different integrals to do this in the order of x dy. And if we did the order dy dx, my arrows are traveling in the y direction. Sometimes we leave on the horizontal and leave on the circle. And then in the middle, we enter along the small circle and leave along the big circle. And then later on, we enter along the horizontal and enter the circle again. And so we would have to break this up into 3 integrals. Once for this part, once for this part, and once for this part. And so that also requires 3 integrals. So what a mess that's going to be, to have to do this using 3 different integrals. But if we did this in polar coordinates, My angles go from 0 over to pi. And if we travel in the direction of the radius, no matter which angle we're at, we always enter along the small circle and we always leave along the big circle. And this is something we can do with one integral. The small circle has a radius of 1. The large circle has a radius of 3. And that's so much easier than what we would have been doing before. And then some stuff goes here in the center that we don't know what that is. But this region is much easier to integrate in polar coordinates. Okay? And so let's talk about how we're going to convert a double integral to polar coordinates. First thing is we're going to do is choose an order of integration. Very, very often, almost every time, the simpler choice is going to be dr d theta. Because if I have any trig functions, I would rather have sine theta or cosine theta or tangent theta instead of having to put it the other way around and having to work with sine inverse theta and cosine inverse, or sine inverse of r and cosine inverse of r and tangent inverse of r. And so I would much rather work with the regular trig functions than the inverse trig functions. And so almost always you want to use this order. There are a few exceptions, but they are few and far between. If you're not sure, try dr d theta first. Okay? Then we have to express the region using polar coordinates. Since we're doing dr d theta, okay, the theta has to be constants, and we're not allowed to wrap around the circle more than once. I'm not allowed to integrate, say, from 0 all the way to 4 pi. That's not allowed because you're counting everything twice because you went around the circle twice. So you can pick negative theta. For example, if my region goes from here to here, I could call this negative pi over 4 to positive pi over 4. And that's perfectly okay. We're allowed to have negative theta to positive theta if that's what my region is. I don't have to break this up at 0, for example. But I'm not allowed to count angles twice. So I'm never allowed to go around a circle twice. When I'm expressing radius, though, radius always has to be positive. So neither the small boundary nor the large boundary is ever allowed to be negative when we're integrating, okay? But because it's the inside variable, we are allowed to have thetas in our formula. So we don't have to have constants for r. R can have thetas in them, okay? And then if we have x's and y's in the formula, we have to convert them by saying x equals r cosine theta and y equals r sine theta. And then this step is unusual. We need to talk about this in a little while. We'll see why later. But the function that we're integrating, we have to multiply that function by r before we integrate it. And then we just integrate it normally. Okay? So let's give an example here. We want to find coordinates to find the volume of the solid under this plane over the annulus. An annulus is a circle with a hole in it. And if we graph this, you'll see what I mean by this. X squared plus y squared equals 1 is a circle of radius 1. X squared plus y squared equals 4 is a circle of radius 2. And so we want to integrate over this entire region here. Okay? All right. My plane is z equals well, it didn't say what this equals. Probably equals 0. So z is going to equal 8 minus 2x minus y. And that's going to be 8 minus 2r cosine theta minus 2r sine theta. Minus r sine theta, not 2r sine theta. All right, so let's set this up. My function is 8 minus 2r cosine theta minus r sine theta. And we multiply the entire function by r. That's at step 4. And my order is going to be dr d theta. Since we're going around the entire circle, theta will go from 0 to 2 pi. And if we travel in the radius direction from the center out to the edge, we always enter the region at a radius of 1, and we always enter the region at a radius of 2. Okay? And so this is going to be the setup to find the volume for this solid. I'll let you solve this. We'll move on to the next example. We want to integrate this by converting it to polar coordinates because I don't want to have to do that square root of 1 minus y squared if I don't have to. Okay? So let's look at what this region is. The y coordinate goes from 0 to 1. And the x coordinate goes from 0, which is down here, or over here, to x equals the square root of 1 minus y squared, which is x squared equals 1 minus y squared, which is x squared plus y squared equals 1. Well, that's a circle of radius 1, but it's only the first quadrant of the circle because we're stopping at y equals 0 and not going down to the negative quadrant. And we're stopping at x equals 0, and so we're not going over here to quadrant 2 either. So just the first quarter circle here. All right, so if we change this into polar coordinates using the order dr d theta, x squared plus y squared is equal to r squared, but we multiply it by r, and that gives me an r cubed. Okay. Theta goes from, the angle goes from 0 just to pi over 2. And the radius starts at 0 and ends at 1. And I hope everybody agrees that this integral is going to be a lot easier to work out than this integral. In fact, I'll go ahead and set this up here. The integral from 0 to 1 of r cubed dr is r to the 4th over 4 from 0 to 1, which is 1/4. And the integral from 0 to pi over 2 of 1/4 is just 1/4 theta from 0 to pi over 2. And that's pi over 8 minus 0. Okay? A lot easier than this integral would have been. If we'd integrated this with respect to x, we would have had an x cubed over 3, and then this would have turned into 1 minus y squared to the 3/2 over 3, and that would have just been awful. It's very nice that we didn't have to work with that. Okay? All right. 2 more examples, and then we'll wrap up. Before we get to them, why is it that we have to multiply by r? What is that step 4 all about? And it comes from the idea that if we were taking the limit of the Riemann sums, we have some point, x comma y, and then we have this delta y and delta x. And so this is the point x plus delta x, y plus delta y. And the area of this little region here is the width times the height, which is delta x times delta y. But we are dividing the region we're looking at into little rectangular pieces. So we integrate a function over a rectangular grid. The rectangles that go from x to x plus delta x and y plus delta y, well, that region is just delta x times delta y. That gives you the area. And then when we take the limit, as this approximation gets better and better and better as the things get smaller, the limit, we can use the dx dy, which is an approximation of this, but in the limit, the approximation becomes perfect. But if we try this in polar coordinates, we're not on a rectangular grid, we're on a polar grid. And my shapes aren't rectangles, they're these little curved regions with straight sides. The sides are straight, but the outer boundaries are curved. And that area isn't just dx dy or dy dx, it's the area is r times delta theta. Because the area of my, what are the analogs to rectangles, if we take a point r theta and move out to a little bit different r and a little bit different theta, r plus delta r, theta plus delta theta, the area of that region that we get, because of the curvature, it's not just a rectangle. It's not base times height. It turns out to be r times base times height, basically. And so to account for this different geometry we have, we just have to multiply by r. And it's just one of those things you just memorize. You have to multiply by r in polar coordinates because this shape has a different area formula than a rectangle. Okay? And you don't have to go down and solve the Riemann sum every time. You just know that as a result of doing the Riemann sum, there's an extra r in the formula. Okay? All right. So let's try a couple of trickier problems. Find the area enclosed by the lemniscate. Oh my goodness. What is a lemniscate? R squared equals 4 cosine of 2 theta. So if we don't know how to graph this, let's pick some angles. And so what we get, when theta is equal to 0, cosine of 0 is 1. So the r squared is equal to 4. So r is going to equal to plus or minus 2. So when the angle is 0, we get a radius of 2, but we also get a radius of negative 2. I can't use negative radius when we integrate. We'll have to rewrite that as an angle of pi and a radius of positive 2. But the formula gives me these 2 points. All right, let's try another one. When theta is pi over 4, then 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0, and so the radius is going to be 0. So at pi over 4, we're back at the origin. Okay? So what happens between 0 and pi over 4? Let's try pi over 6. That's an angle between pi over 4. 2 times pi over 6 is pi over 3. Cosine of pi over 3 is root 3 over 2. 4 times root 3 over 2 is 2 root 3. And so r squared is 2 root 3. We get plus or minus the square root of 2 root 3. Well, that's kind of messy because it's a square root of a square root. But that works out to be a little bit less than 2. And so what happens is as the angle gets bigger, the radius gets smaller and smaller and smaller until it comes all the way back into the origin. And then what will happen is then the shape comes back out on this side and completes the figure 8 like so. Okay? If we kept plotting some more points. Well, if we want to find the area of enclosed by the lemniscate, we can just look at this area and multiply by 4. Total area equals 4 times the first quadrant. And the first quadrant area happens between 0 and pi over 4. Once we get to pi over 4, we're back at the origin, and that closes up this region. Okay? So we can set this up in the order dr d theta. Okay? If r squared is 4 cosine of 2 theta, then well, let's talk about what's going on here. The angle goes from 0 to pi over 4. The radius goes from 0 out to where we reach this radius, and r by itself is going to be the square root of 4 cosine 2 theta. Now, to find an area and not a volume, we would normally just put a 1 here, but the polar rules say that no matter what we put here, we have to multiply it by r. And so an r goes here. 1 for area times r for polar. Let me write that out. Times r for polar. Okay? And that square root turns out not to be as bad as you think it might be, because when we integrate r dr d theta, we get r squared over 2, and the square and the square root cancel each other out. And so when we solve this, it's going to work out pretty nicely. Okay? All right, last example. We want to find the area in the first quadrant enclosed by this cardioid. 1 plus sine theta. All right, so let's make a table of values again, so we can kind of plot this out. When theta is 0, the radius is 1 plus sine of 0, which is 1. So that takes me out to 1. Okay? When theta is pi over 2, the radius is 1 plus sine of pi over 2, which is 2. That's actually 2 units up here. And since the question is asking about the first quadrant, this is really all we need. But I'm going to keep going for a moment. When theta is pi, the radius is 1 again. 1 plus sine of pi is 1 plus 0, which is 1. So the angle is pi, but the radius is 1. And then when the angle is 3 pi over 2, sine of 3 pi over 2 is negative 1. 1 plus negative 1 is 0. And so the radius comes into 0. And so this looks like an upside down heart, which is where the name cardioid comes from. We want to find just this area here. So the area is, we'll use dr d theta for the order. We put an r in here. Once again, this is 1 for the area, and then r for the polar coordinates. Since we're looking at the first quadrant, my angle goes from 0 to pi over 2. And my radius starts at 0 in all cases, and then leaves along the cardioid. So from 0 to 1 plus sine theta. Okay? All right. Good luck with this section. I'll see you guys on Friday. Take care.